Hello everyone. Once again on behalf of the State Council of Science, Technology and Environment, I once again invite all the viewers to this online class that is conducted especially for the class 10 students. Last class we have talked about some of the physical properties of metals and non-metals. Now we are going to do the chemical properties of metals and non-metals. In identifying elements into metals and non-metals, we have said that metals, they are generally hard and non-metals, they are generally soft. But here we have some exceptions, that is, some elements which are metals but they are soft. Example, sodium and potassium, they are soft. And also here we have exceptions. Diamond, which is a non-metal, it is very hard. And also we have said that metals have high melting points and boiling points. And here, as sodium and potassium are soft, so they will have low melting points and boiling points. So here we also have the exceptions that sodium and potassium, as they are soft, so they have low melting points and boiling points. And in the case of non-metals, we have said that they generally have low melting points and boiling points. But here also we have some exceptions, and we have that the carbon, silicon, boron, they have high melting points and boiling points. So from these exceptions that we have, the physical properties of metals and non-metals, they are not enough for us to differentiate between metals and non-metals. So that's why we need to study the chemical properties of metals. Now in the chemical properties of metals, we will have a look at the action of metals with oxygen, with water, with dilute acids, and finally we will study the reaction of metals with solutions of other metal salts. Now, as we have said that metals, they donate electrons, but some metals, due to their large size, the valence electrons are not tightly held to the nucleus. So in that case, they give away the electrons more readily compared to other metals. So those metals which can give more readily their valence electrons, they react faster than the other metals whose valence electrons are more attracted by the protons in the nucleus. So we can arrange the metals according to their chemical reactivity, and the arrangement of the metals in a vertical column in the decreasing order of their chemical reactivity is called metal activity series. So what do we mean when we say metal reactivity series? So in the metal activity series, the metals are arranged in a vertical column in the decreasing order of their chemical reactivities. And it is given by this. We have this: potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, and coal. So this is the metal activity series. So as you go down, then the chemical reactivity also decreases. So this will be the decreasing chemical reactivity. So here, as you can see, K will be the most reactive element and coal will be the least reactive elements. And the elements above hydrogen are more reactive, and below hydrogen they are less reactive. Actually, hydrogen is a non-metal, but here it just divides this activity, the chemical activities of these metals. And also hydrogen, it also shows some properties of metals as it forms hydrogen ions. That is, it loses electrons to form the hydrogen ions. Now, first of all, let us study about the action of metals with oxygen. Now, the general formula we have when metals react with oxygen, they will give metal oxide. This is what will happen if a metal reacts with oxygen in general. But it also depends under some conditions. But first of all, let us take an example. Let us first take when potassium reacts with oxygen. Now, as potassium is very reactive, so when in air, even at room temperature, it will react very fast with oxygen to form potassium oxide. This will be the balanced chemical equation. And here also, if you take this sodium is also still very reactive. So if you react sodium with oxygen, this is also at room temperature, it will give sodium oxide. And as you go down this activity series, the chemical activities also decrease. So that's why when we react magnesium with oxygen, we have to apply heat so that we will get magnesium oxide. And as you go down again, suppose you react this zinc with oxygen. At room temperature, it will not react with oxygen, as zinc is less reactive compared to these elements on top, which are more reactive. So here, when you react with zinc, you have to heat at higher temperature. And what will you get? You will get zinc oxide. And again, as we go down, let us have a look at when we react iron with oxygen. Iron, when we react with oxygen, what will we get? Here iron, as it is less reactive, so it will not react with oxygen even when you heat it at just temperature which is not that high. So here you have to apply strong heating, and when you heat this at a very high temperature, you will get iron oxide. But iron, it has two valencies. One which is of valency 2, it can also have this valency 3. So when this iron with valency 2 react with oxygen which has valency 2, it will give this iron 2 oxide. And when iron with valency 3 react with oxygen, it will give this iron 3 oxide, which is Fe2O3. So here, when iron reacts with oxygen, it will be a mixture of these two oxides of iron. So in this case, we'll have a mixture here. Fe2 with this one will be Fe3O4. So this is what we will get when we react iron with oxygen at a very strong or very high temperature. And finally, lastly, we'll have a look when we react copper with oxygen. Here, copper, as it is very less reactive, from this reactivity series you will see that copper is very less reactive. So even in strong heating, it does not react with oxygen readily. So you have to do the strong heating for a long time. So we have to do the prolonged strong heating. So when you heat this at a very high temperature for a long time, you will get the copper oxide. So this is what happens generally when we react metal with oxygen. We will get metal. Let us have a look at the nature of the metal oxides. Suppose we take one metal oxide and suppose that metal oxide is potassium oxide. Suppose we dissolve this potassium oxide, then what we will get? We will get potassium hydroxide. And in this beaker, if we dip a red litmus paper, what will be observed? We will observe that this red litmus paper will turn blue. So here, this red litmus paper turns blue. So this shows that this solution is basic in nature. And similarly will be the case when you dissolve sodium oxide or magnesium oxide. You will get that the solution will be basic in nature. And mostly all metal oxides, they are basic in nature. So that's why metal oxides, they are commonly called as basic oxides. And we have this definition. We have this definition of basic oxides. What do we mean by basic oxides? Basic oxides, they are those metal oxides which reacts with acid to form salt and water as the only products. Those metal oxides which react with acids to form salt and water, they are called as basic oxides. So example, we have this sodium oxide. When it reacts with acid, let's say hydrochloric acid, it will give sodium chloride and water. Sodium chloride, which is a salt, and water. But there are also metal oxides which reacts with acids as well as with a base which is soluble in water to form salt and water as the only products. So those type of oxides, they are called amphoteric oxides. So in other words, we can say that amphoteric oxides are those metal oxides which are both basic as well as acidic in nature. So example, and these amphoteric oxides, example we have that zinc oxide. Suppose it reacts with an acid, it gives zinc chloride, which is a salt, and water. And this same metal oxide, it also reacts with bases or with alkalis, bases which are soluble in water. Suppose we take sodium hydroxide, it will give this salt, sodium sincate plus water. So as you can see, this metal oxide, which is zinc oxide, reacts with acid as well as a base to form salt and water as the only products. So such types of oxides, they are called amphoteric oxides. As you can see here, zinc oxide, when it reacts with an acid, it behaves like a base. The product is salt and water. And when it reacts with a base, it behaves as an acid. And the product will be again salt and water. And that reaction, that acid reacts with base to form salt and water, that we call the neutralization reaction. Now let us have a look at the action of metals with water. What will happen when metals react with water? When metals react with water, we will get either the metal oxides or metal hydroxide plus hydrogen. And here also, the rate of reaction will depend on the chemical reactivity of the metals. That is, more reactive metals will react faster and they will react even at normal conditions. But these less reactive metals, they may react at higher temperature or they may not react at all. So let us take the example when this most reactive metal, which is potassium, reacts with water, we will get potassium hydroxide plus hydrogen. Here, even in cold water, potassium will still react with water, and the reaction is very fast. This is due to the high reactivity of potassium. But what will be the case when we react zinc with water? Zinc will not react with water at normal conditions, but when you heat this zinc, and you pass steam over heated zinc, then when you pass steam over heated zinc, you will get zinc oxide plus hydrogen. So as you can see from here, zinc does not react with water at normal conditions. That's why it is less reactive compared to potassium. And now we will we will have a look at the action of metals with dilute acids. When metals react with dilute mineral acids, this is the general formula that we will have. We will get a salt and with the release of hydrogen. And here also the same thing will happen about the rate of chemical reaction. More reactive metal will react faster, and the less reactive metal will react slower, or may react at higher temperature, or there may be no action at all. And for example, if we take this metal, which is magnesium, suppose you react it in dilute sulfuric acid, you will get this salt, magnesium sulfate, with the release of hydrogen gas. And suppose you take this metal, which is below the activity series. So when you take copper and you react with sulfuric acid, here we will see that no reaction will be taking place. No action will be taking place. So this shows that copper is very less reactive. So these are some of the reactions that we are taking in about the action of metals with dilute acids. Next class we will study about the action of metals with salts of other metals, with solutions of other metal salts, and we will study more about the occurrence of metals. For now, we will stop here. We will see you again next class. So I hope you have understood. Thank you.